16, Control Theory and Optimization. My name is Enrique Zuazua. I am a Humboldt professor at Friedrich Alexander University in Erlangen in Germany, and it's my pleasure to be the chair of this session. Our speaker now will be Professor Coralia Cartis. She will be lecturing on the evaluation complexity of algorithms for non-convex optimization. Coralia is a Romanian mathematician at the University of Oxford, whose research interests include compressed sensing, numerical analysis, and regularization methods in math optimization. At Oxford, she is a professor in numerical optimization in the Mathematical Institute and a tutorial fellow of Balliol College. Coralia, the stage is yours.
Thank you very much. Thank you very much for this introduction and for this honor. I will now share my screen. Okay. Oops. All right. Today I will talk about my long-term collaboration and our results with Professor Nick Gould and Professor Philippe Thuin. They concern the optimization of functions of multiple variables where the underlying function is smooth. We are trying to develop general methods for these functions that can have all shapes and sizes. So in 2 dimensions, you can see here an example where we can have many local minimizers and one global one. Or in this right-hand side picture, you can see that we have just one stationary point, one minimizer in this narrow valley, but still we have a non-convex landscape. So anything can happen. So how can we design algorithms that can solve these problems? Well, because of the smoothness of the function, we are going to focus here on some of the most scalable methods, the ones that use derivatives. And so they can only really guarantee to be able to find a local minimizer of such non-convex landscapes. So we are going to just aim to try to find a point with a 0 gradient, so stationarity, and local convexity at a local minimizer. So the second derivative should be positive, definite or positive, semi-definite. These are very successful methods, and that's why in practice, that's why I'm talking about them. And how they proceed, all these derivative-based methods, they can start from an arbitrary initial guess of the solution. So from an arbitrary x0, and then they will generate points in Rn, okay, in our domain, that are better and better approximations of a solution. How do they do that? Well, by approximating our complicated function f around the current iterate xk by a simpler model. This model could be a linear or a quadratic approximation of the function. And because we are allowing ourselves to use derivative information about the function f, we are going to, for example, assume they could be Taylor approximations. And we are going to minimize these models to find an improved guess of our solution. So we are going to find SK as a minimizer of this local model and then somehow construct the next iterate from that. And then when we get a sufficiently small gradient at an iterate, then we can terminate and maybe we can even certify second order optimality. So let me pin down these models again. Let me write them down. So if I write them down, I get the first order Taylor approximation of f. And if I think that I'm going to minimize this linear approximation of the function around the current point, subject maybe to some normalization, then my direction is the negative gradient. And so these methods are essentially first order methods. So they use first order, so 0 orders of function evaluations and first order gradient evaluations of my function. And then they generate, say, gradient descent directions. Or if I allow myself to use second order approximations of my function, so quadratic approximations, I then have to use second order information about my function at the current iterate. So to be able to obtain that, Then I can construct my model, and when I find a direction that minimizes this model, then I will obtain a Newton-like direction, a second-order-like method. Now, if I just construct these minimizers of these local models and I append them to my current guess of the solution, I will not get a method that converges from an arbitrary starting point. Because we are trying to solve very general problems in our approach as optimizers, we try to tackle a large class, we would like to provide robustness. So we would like to tell the user that he can indeed have a convergent method from any starting point. And so we have to be a bit more careful and safeguard this direction SK by some techniques that ensure this kind of convergence from any starting point. And the classical ways to do that is to use something called a line search or a learning rate, as it's often called now in the machine learning literature. So what you do is that you're going to cut your search direction by some fraction to ensure that the function goes down or that you make progress in decreasing your objective f at each iteration. Similarly, you can say, I'm going to only trust my model in some region of trust, and then similarly, you can proceed with that and adjust this region of trust in the run of the algorithm. So these are, so these kind of directions obtained from minimizing local models coupled with some safeguarding strategies ensure this kind of convergence. Indeed, for this kind of strategies, first order methods, so gradient descent, or second order method, Newton-like methods, you can get this kind of global convergence results, meaning from any starting point, you're guaranteed to find a limit point of your iterates to be a stationary point or a second order local minimizer. These results have existed for quite a few years in the nonlinear, non-convex optimization literature. Now, another type of analysis that we can give to these classes of methods is that if you are sufficiently close to a solution, then these methods will be attracted to a minimizer and you can quantify the rate. And these are properties that one studies often, even in the first year or second year of a mathematics undergraduate degree. So for example, you can show that the gradient descent method close to a solution has a linear rate of convergence, and a Newton type method is very fast. So it's quadratic close to a solution. What we have not had in the non-convex literature very much until recently is a possibility to kind of merge this kind of results, the global and the local, in the sense that for all the global convergence results that can guarantee that from any starting point you get a sequence of iterates that are stationary in the limit, you are not able to say until recently how fast is this rate. So locally, if you're sufficiently close, you can say how fast it is. But if you're far, you just don't know. In the convex case, you know these answers for a while. But in the non-convex literature, people didn't think this was possible. So what do I mean here? And this is the topic of this talk is to talk about global rates of convergence of non-convex optimization algorithms. So I want to start from anywhere, and I want to find out how many iterates do I need to take to generate an approximately small gradient. In other words, practically, how much do I need to stand in front of my computer to wait for an answer from my algorithm? This is really the practical question that one user asks. Convergence may happen, but how long will it take? Equivalently, we can formulate this question in terms of worst case evaluation complexity. So I'm asking here how many calls to the oracle, to the black box that gives me values of f, values of the gradient of f, and values of possibly even the second derivatives of f. How many of these calls do I need to generate an approximately small gradient, a gradient below some tolerance epsilon, any tolerance epsilon? And how long do I need to stay in front of my computer to wait in terms of calls to this black box? So oracle complexity is another name for what I'm doing here, or evaluation complexity. This matters because this kind of model of complexity matters in this case because, again, we have a very general class of problems that can come in all shapes and sizes. And also because for some of these problems, this kind of evaluations is the dominating cost in your problem rather than the cost per each iteration, the computational cost of each iteration. Indeed, I will try to tell you something about what do we know about these standard methods that I started with. What do we know about steepest descent and Newton? What is their global rate of convergence? What is their worst case evaluation complexity? And then talk about some better methods than what we know, and then try to input more derivative information in my methods and see what happens with the complexity, and then ask all sorts of questions about what kind of critical points I can find, and then try, if time permits, to get to the modern questions of what if I have no derivative information, which is very much the remit of stochastic problems that we encounter nowadays in machine learning. So let's begin our journey. Negative gradient descent or steepest descent methods. So I move along the negative gradient at each iteration. I globalize, I safeguard my method with anything you prefer, line search trust region. This is what we can show. If the function f is continuously differentiable and the gradient of f is Lipschitz continuous, then to generate a gradient that goes below any tolerance, user-provided tolerance epsilon, requires at most epsilon to -2 function and gradient evaluations. This corresponds to a sublinear rate of convergence. So if I start from anywhere, I'm sublinearly convergent. If I'm sufficiently close, I'm linear. This makes sense. It concords with the local results. If I look at what this bound has in it, I can see that it depends, of course, on the distance of how far my point is, my starting point is to the solution. This lower bound f low on my function. It depends on the Lipschitz constant in the bound, but of course the Lipschitz constant is not used in these algorithms. All these line searches and trust regions are assumed to be adaptive strategies. What about if I go to second order methods? So if I go to Newton's method, what I find is that, again, whatever safeguarding strategy I use for the Newton direction, I end up requiring a bound that's of order epsilon to -2 again, so sublinear rate, to drive the gradient below epsilon. So this is the surprising aspect here, that in terms of upper complexity bound, both first order and second order methods seem to coincide, despite the fact that we know that locally gradient descent is linear, and Newton is our favorite method, the fastest method we use, namely is quadratically convergent locally. So globally, this is not so efficient. But you may say, these are just upper bounds. Are they sharp? Yes. So we were able to construct sharpness examples. So here's the gradient descent. Let's start with that. And I construct a line search, the best line search I could do. Namely, I minimize my function at every iteration along the negative gradient descent step. So the most expensive one, but I do the best I can and show that still bad things can happen. So if I do something more inexact, bad things will still happen. So here's a two-dimensional example and that we constructed. And here are the iterates of the method. So you can see that they oscillate along a valley. And on this example, you can show that the steepest descent will take precisely epsilon to -2 iterations to drive the gradient below epsilon. This is a function that we can show. It has a globally Lipschitz continuous gradient, so it satisfies the conditions for which we have the upper bound, showing the sharpness of this result. Same for Newton. Here's another two-dimensional example that now has even more smoothness. So both the gradient and the second derivative of this function are globally Lipschitz continuous. And despite this smoothness, this bound is yet again attained. These are both two-dimensional examples. So the question arises, is there anything better? Is there any better first or second order method that is achieving a better worst case complexity? And we will focus on second order type methods for now. So let me tell you about cubic regularization. Let me give you a very brief refresher of a property that you are familiar with from your analysis courses. If I have that the second derivative of a function is globally Lipschitz continuous, then at any point xk, and for any direction s, I can upper bound my function by this approximation. This first part is just the second order Taylor approximation. And this here is a regularization term, where the weight on the regularization is the Lipschitz constant of my second derivative matrix. And what we see here is that, yes, we have the Taylor model. So this will be a Newton type method, and it's regularized. And because it sits above the function, the idea is that if I minimize this potentially non-convex, because this matrix is not guaranteed to be positive definite, if I minimize this potentially non-convex third order model of my function, then I force the function to go down. So I force decrease in f from its current value of f at xk. So this approximation here, we can just think of it as a new local model. And indeed, it turns out that if you do that, if you minimize this model at every iteration and find your direction, then though it's a global minimization we are talking about here, and it's possible but expensive, you can show, and it was shown by Nesterov and Poyok, that this method takes at most epsilon to minus 3/2 function evaluations and gradient and Hessian evaluations to drive the gradient below the required epsilon tolerance. So still a sublinear rate, but better. However, this method uses the Lipschitz constant of the second derivative matrix, which in a practical method we don't have. Also, it assumes this global minimization of a non-convex local model at every iteration. So can we make this method practical? Can we make this method implementable? That was our first question. And what we did was to replace the Lipschitz constant by a regularization weight, because we may not have the Lipschitz constant in a real application, and we may not even know that it exists. The other thing we can allow here is to allow an approximation to the second derivatives, but I will not focus on that today. How about how accurately we need to minimize this non-convex model? Very mildly. It's sufficient to just get some decrease from your base point, s equals 0, and to get an approximately small gradient. We can think of the step as something as with k decreases. And so as I proceed in my algorithm, at every iteration, I will make this subproblem minimization more and more accurately. But the main idea here is that the model, I just minimize the model to first order local minimization. Then, because now I dropped the Lipschitz constant, I no longer know that this model sits above my function at every iteration, like on the previous slide. I no longer have this property. So then I have to check it. I have to check that when I minimize the model, I've minimized my function. And that's what we do. When we measure this function rho, we evaluate f at the new point, and then we check that when I minimize my model, I've decreased my function. So if this measure of progress is positive, so I've minimized f, then I take my step. And if I've not managed to decrease f at my new point, then all I can do is to adjust my weight here. So I adjust this regularization weight, that's now an algorithm parameter. Namely, if I shrink it, the step increases, and if I increase it, the step shrinks. So what I wanted when I don't manage to make progress is to shrink my step because I've gone too far. These are essentially Taylor models. So if I'm close to my base point xk of the approximation, then I'm guaranteed to decrease my function. So all I have to do is to increase sigma sufficiently. So I keep doing that until I manage to decrease f, basically. Otherwise, yeah, I stay at the same point. This part does not need to be recomputed. Just this sigma is increased, and then I have to recompute the step. All right, and sometimes I allow this sigma to decrease so that I don't unnecessarily shorten the step in the run of the algorithm. These are technical details, but basically the idea is that I can get rid of these Lipschitz constants and make the algorithm adaptive and practical. Now, what happens with the performance? You know, is this competitive with state of the art? Here in these pictures, I showed you one of these cubic models to convince you this is a non-convex local model. And here on the right plot, I show you its performance on a collection of nonlinear test problems against some state-of-the-art variant of trust region. And this is a performance profile Namely, it looks at the average performance of the algorithm on this text collection, and it looks at the fraction of the problem on this horizontal axis. I plot the fraction of the problems that on which the algorithm is within a certain alpha percentage of the best algorithm. Simply said, the higher the curve here, the better the performance of the method. And you can see that the cubic regularization variance based on the method I've described beat trust region, beat state-of-the-art methods. These are very kind of preliminary numerics, but what you find is if you make very sophisticated implementations of both trust region and cubic regularization, you find that each one of them has its benefits on different problems, and they are essentially comparable. And for example, regularization would do much better on constraint problems. They are simpler to deal with because you don't have constraints in the subproblem. Trust region would do better on constraint problems. These are kind of more technical details. But essentially, we get encouraging practical performance. How about complexity? Let's return to our complexity story. Though we've made this theoretical algorithm practical, what we find is that its worst case complexity is preserved. So the bound obtained by Nesterov and Poyak for the idealized method is maintained. We still retain this epsilon to minus 3/2 bound. And here we have this Lipschitz constant of the Hessian coming in and the distance to the solution, similar to what I showed you in the gradient descent bound. So it's a typical bound. Now, I will dare even tell you something about the proof. I dare to do this. I've seen it done in some of the talks this morning, like Alice Guillonet's talk. So I will dare. My proof is much simpler than what she presented. So let me just give you the key ingredients that give us the better complexity. At every iteration where I make progress, where I take my step sk, I have to have some form of sufficient decrease. So I've decreased my true function sufficiently. Indeed, then my measure of progress rho is positive, sufficiently positive. So the decrease in f is a multiple of the model decrease. And we see that from this condition trivially and the expression of m, this is bounded below by the length of the step to power 3. Now, what I need to do is to connect this sk here to the length of the step. If you don't care about this proof very much, it doesn't matter. So you can just ignore me for a moment. So I will tell you now that for this cubic regularization, we can show that the step is long enough, is greater than the square root of the gradient. If sk was a descent-like method, this would just be the gradient. The gradient is not as long as the square root of the gradient when we get in the regime that we care about, where these lengths are less than 1. So this is better. This is better, and it's better at every step. So it's going to be better in the worst case. So then we can say the following. While the gradient is above epsilon and I have not terminated my method, then I know that this the length of the step is above square root of epsilon. So here I have that the function decrease is at least epsilon to the 3/2 at every step when I make progress. So I get this decrease proportional to epsilon to the 3/2. Now I have to make sure that I don't have too many steps where I make no progress because my step was not giving me decrease, and I just increased the regularization weight, and we can show that that doesn't happen too much. And so we end up with summing up these steps, this decrease at every iteration, and saying that then, I cannot have too many of these steps where I make progress because I have a finite distance between my starting point and the lower bound of my function of f star. So summing up all these decreases tells me how many steps I can take, namely something proportional to epsilon to minus 3/2. Now you can say to me, is this bound sharp? Yes. So we can construct even a one-dimensional function on which this bound is attained. And here I plot this one-dimensional function. In blue is the function decrease. You can see very, very small undulations of my function. And this is in green is the gradient. It has only one stationary point. Here in this right-hand side plot, I plot in blue the second derivative, and in green the third derivative, showing that it stays bounded just barely. So this again is a function that has Lipschitz continuous gradient, Lipschitz continuous second derivative, so it belongs to a class for which the upper bound held. So it's a true sharpness result. Is it optimal? This sharpness does not establish optimality. So we showed that it is optimal as well. So for second order methods, there can be no better method from a worst case complexity point of view. This is it. There can be no better bound. And the optimal and the cubic regularization attains this bound. So we constructed a large class of problems, and for every problem we can construct an example that on which Newton type methods attain this epsilon to minus 3/2 bound. Also, there is another type of examples coming from Carmon and Ducci and others that show the following result, that there is a worst function in the world on which every Newton type method attains this epsilon to minus 3/2 bound. So it takes at least epsilon to minus 3/2 iterations. This function, though, is not unidimensional, but it grows with a number of iterations. So it's a different type of examples, high dimensional, but growing with iterations. Okay. So this is my summary. I'm not done, but this is where we are at. Let me summarize what we have found. If the function f has sufficient smoothness just in terms of Lipschitz continuity properties of the gradient or second derivative, so I don't assume anything on convexity of f, then steepest descent is epsilon to minus 2 iterations to drive the gradient below sub epsilon 1. Newton and other variants of Newton are epsilon to minus 2. Cubic regularization is better. Recently, spurred on by these properties of cubic regularization, people constructed truss region variants, line search variants that have the same complexity, that kind of mimic the cubic regularization method to try to get a better bound than epsilon to minus 2. What about second order criticality complexity? So how many iterations do I need to take of my method to achieve both of these conditions? When I can't do it for steepest descent because I don't have second derivative information, but for all the other methods, I get the same epsilon to minus 3 in terms of also achieving this property of approximate local convexity. So to second order, these methods kind of look similar. And as I said, we know all these bounds are sharp and cubic regularization is optimal. Now, I want to ask the following question. Can I do better? What if I have higher order derivative information? And can I, for example, improve these second order bounds here? Are there methods that have better complexity to second order? And this is what I want to try to answer next. So for that, let me just give you cubic regularization again and showed you how I'm going to generalize this method. So I had Taylor to second order, and here was the cubic power of the step. So 2 plus 1. And here I'm pinpointing the exponent. So again, here is like 2, so the same power as here. Here is 1 for getting second order criticality. So the conditions of the minimization of the model. Then here, what in fact I was doing with my slightly strange measure of progress, I was measuring progress with respect to minimizing the second order Taylor model. So now I'm going to replace this T2 from cubic regularization with TP, P larger than 2. So I'm going to assume that I have third order tensor information about my function at xk. So I have higher order derivative oracles. So if I do that and I replace T2 by TP, then I regularize here by the P plus 1 order of the step. I change my model minimization conditions accordingly, and I change P here. And all the other ingredients stay the same in the algorithm as before, as for cubic regularization. What can I show? I can show that if my function is sufficiently smooth, I have access to these higher derivatives, and the pth order derivative is Lipschitz continuous, then for first order criticality, to drive the gradient of f below epsilon 1, I take this many iterations, so P plus 1 over P, and I also can certify second order criticality. And it's more useful to look in this table here. So if I have just cubic regularization, I get this complexity as before. If I have third order tensor information, I improve the complexity. I get from minus 3/2 to minus 4/3, and so on and so forth. I continuously improve this complexity to first order, essentially tending towards epsilon to minus 1. And furthermore, I improve the second order criticality bound again tending to epsilon to -1, so I can depart from this epsilon to -3 bound. All these bounds are sharp, and the first order bound here are also optimal for methods that use fifth order derivatives in the algorithm. This was shown in the same paper of Carmon, and we have lots of sharpness examples in our paper as well. Is there anything else left to say here? I just want to mention that we don't use additional derivatives in the subproblem. So the evaluation cost is just also the number of subproblems I need to solve, but not the computational cost of each subproblem. But those don't do calls to the box. I also want to say that trust region methods don't have this good complexity to higher orders. We have estimated that, and we cannot get anything better. I won't tell you much about the proof, but it's very similar to ingredients to before. I have to ensure sufficient decrease, which now will be proportional to the step to p+1. I have to again ensure that the step is long enough. So now it's proportional to 1 over p, the step. Here I should have norms, and so on. So long step and sufficient decrease are again the keys to success in deriving the complexity of these methods. Now, if I have higher order information about my function in terms of derivatives in the algorithm, then I can start thinking about another kind of answer. And here I need to pause for a moment to explain. So until now with my methods, I have attested at the end to get an approximately first order critical point, so sufficiently small gradient, and second order, so approximate local convexity. Now, if at the end of my algorithm, I have the gradient below epsilon, and I have a positive definite second derivative, I am definitely, zero gradient and positive definite second derivatives corresponds by sufficiency to definitely a local minimizer. I know for sure it's going to be a local minimizer. But if the second derivative matrix is only positive semi-definite, I may have zero eigenvalues of my second derivatives. And then I cannot say for sure that that's a local minimizer. To find out, I need to go to higher derivatives. I need to go to third order derivatives. What is the third order necessary optimality condition? If along directions corresponding to zero eigenvalues of the second derivatives, I also have that the third order tensor along those directions is zero, then I have a local minimizer. So those third order terms get canceled out, then I can stay, I have a local minimizer. I can guarantee that. So I can when I have this third order information in my methods, I want to ask this question: can I find approximate third order criticality? So can I make the third order derivative small? Well, then I have to minimize my model, my cubic my higher order regularization model. I have to minimize it to third order criticality approximatively. And here's a condition for doing that. But then the good news is that indeed I can estimate this complexity to third order. So I can assess how many iterations will it take to find an approximate third order critical point. And that looks at indeed third derivatives of my function to be sufficiently small along directions corresponding to small eigenvalues of my second derivative matrix. So that's good news. But then I say to myself, okay, let's try to make this even harder. Because if I have even higher order derivative information of my function, like fourth order information, like I was assuming before, what can I say about fourth order critical points? Well, I don't even know what fourth order criticality is, and how can I verify that? Well, here's a horrible looking slide, and I'm putting it up just to show you that it gets very complicated. So we can derive fourth order criticality and higher order, and we have done that by looking at algebraic paths. From the current point along algebraic polynomial paths, we can say, well, if I have a local minimizer, I want my function to not be decreasing along this algebraic paths around a local minimizer. And if I then calculate what happens to expansions of my functions along this path, I get these horrible looking expressions, polynomial expressions. So I get conditions that if I'm on kernels of lower dimensional derivatives, then I get semi-definite forms for the last derivative I'm canceling. So they look pretty horrible, and I could never attest to this in an algorithm. And the good news is that even using those expressions, the bad news is that even looking those expressions, if I then try to say, well, can I disentangle them? Because the good news for first, second, and third order criticality of local minimizers is that the good news is that I can disentangle. I can say, well, I have a small gradient. I just satisfy that. Then I can try to satisfy local convexity. Then I can try to look at third order forms, and they are all disentangled. For fourth order conditions, all lower derivatives appear in this kind of polynomial, in this kind of polynomial expressions for which I have to show non-negativity on intersections of lower dimensional kernels. So if I then try to say, well, I just want the fourth order derivative to be positive semi-definite on the intersections of lower dimensional kernels, this is a very, very weak condition that's not really giving me anything meaningful. So I have to deal with this very complicated expression. So again, I cannot do this in the algorithm. So what we had to do was to find out some conditions, some optimality measures that are suitable for algorithm use. And what we did was to look at a very simple one. So to go from those complicated expressions to something very simple that looks at the maximal change at a local minimizer between the value of f there and Taylor expansions of qth order, the order to which you want to certify criticality. And that's our criticality measure. We can show that at a local minimizer, if you look at this discrepancy between the function value and Taylor expansions of up to order q around a ball, in a ball of size delta around the minimizer, that measure divided by delta to j goes to 0 as delta shrinks. Okay, so I don't expect to see change in these Taylor expansions if I look at smaller and smaller balls around my minimizer. And to convince you of this measure, if I calculate this discrepancy to order 1, then I get that it's just a multiple of the norm of the gradient of size delta. For order 2, I also recover a second order condition of a criticality condition. So local convexity multiplied by the size of the trust of this region of trust squared. So then if I divide by the appropriate power of delta, then I recover exactly this measure with my usual criticality conditions of small gradient and positive semi-definite second derivatives. So to first and second order, we coincide to be 4, and third order and higher is something slightly different, but something that we can use in the algorithm. And indeed, with these measures, I can construct now regularization algorithms with the same models, regularized models as before, but now I check a different optimality measure instead of small gradient and local convexity. I check this different phi measure. I check that that's sufficiently small up to order q. And now I have to also deal with what is a good size in which I check my criticality measure. In size delta, what is a good size on which I can testify a good minimizer. That has to be suitably small. So I have this additional algorithm parameter, but we can do it. And what we end up with is something surprising, maybe not, it's not going to be so trivial, but it's analyzable and it's surprisingly short. Short now, wasn't short when we started with this. That is for higher order than 2, we have this kind of complexity for regularization methods with this new optimality measure based on phi. So it's a criticality measure. It's an optimality that depends now on Q, which is the order to which we can certify criticality, and a usual fraction to be 4, depending on the regularization order. Okay, so these bounds are also sharp, and I could talk more about this. Similar ingredients for the proof, but now in terms of phi and delta. Trust region, we can generalize to higher order trust region, but not line search methods. They have very big problems that do not allow us to go to higher than, say, 2, 3 orders. We cannot do it. Trust region doesn't look as good for complexity. It has this kind of complexity for Qth order criticality. So it's not as good as regularization methods, which really come out as best methods for using from a complexity point of view in different regimes. So I'm soon coming to the end of my time. I wanted to say a few words about regularization methods in terms of universality, which is a term coined by Nemirovsky and Yudin and Nesterov that looks at decreasing the level of smoothness of my function. So until now, we assumed Lipschitz continuity. But what if I try to go towards the non-smooth regime and I don't even know that my function is exactly Lipschitz? What if it's just Holder continuous? And in that case, you can think here for simplicity, and due to lack of time, that here R is like P plus 1. So we can have another regularization variant with different conditions. We have to be even more careful with the length of the step. I won't have time to go into it. But what I can do is to allow my function f to no longer be Lipschitz in the pth derivative, but just Holder with exponent beta. And what we find is that the complexity then to first and second order criticality changes appropriately depending on the P is the order of the Taylor expansion of the derivatives I use in my algorithm, and beta P is the Holder exponent. But what I want to emphasize here is that in the regularization method, in the algorithm, the practical algorithm, I don't use the exponent. So I regularize by, say, the P plus 1 order of the step, as usual, and I can apply it to functions that are no longer Lipschitz continuous in the pth derivative, but Holder continuous. I don't know this Holder exponent in the algorithm at all. I don't care. I don't need to know it. I can run the algorithm. The complexity will depend on it appropriately. So the algorithm adjusts to the smoothness of the landscape. I don't lose much, and I can run it on these less smooth functions that are just Holder continuous. And I think, just a minute, I think maybe left. This is a Holder function, Holder continuous function to first order, and you can see that it's not so smooth, it's barely smooth. I wanted to just say that we can further expand this. Sorry, I think these methods to the case where we don't have derivative information at all. So in that case, what we have is we have approximate first order, approximate second order derivatives. We can go higher than that, but we can, for simplicity, just talk about first and second order. And we can assume that they are not even close to the true derivatives with some probability. So I have good derivatives in some iteration and very bad derivatives or arbitrarily bad on others. So just with some probability, these derivatives are sufficiently close to the truth. And again, we can get then probabilistic algorithms. So now we are really at the other extreme of very inaccurate methods. And we can again recover the good complexity for second order, for cubic regularization, namely epsilon to -3/2, provided that more than half the time I see these good enough derivatives. So if I have good models, more than half the time, I get the same complexity, I get almost sure convergence, the same complexity as in the deterministic case. It just changes by a constant fraction depending on the derivatives being good, the probability of the derivatives being good. Okay, so this applies to stochastic gradient and other methods that sample derivatives. I don't have time to go into that now. I want to finish by showing you a book that is coming out now. It should be out. It's available on pre-order, where some of these results are included. And of course, my papers that include much more on the stochastic case as well. Thank you very much for your attention.
Thank you, Coralia, for your very interesting talk. We don't have time for questions now, but they can be formulated in the Discord platform, and I'm sure you will be happy to interact with those that are interested. Thank you again for this excellent survey presentation. Topics are relevant, and I'm sure this will influence further research on the topic. Thank you.
Thank you very much for this opportunity. Thank you.